I finished maybe early a bit, and actually this is intentionally because I have another Zoom meeting in 10 minutes actually. So excuse me for this few minutes before the lecture.
Yeah. I think it's today's talk is also important.
Yes.
I have one question. Yeah. This is very clear for how to derive the fundamental solution. I have a question: is that if we have some the parameter inside the operator, like the heat conduction problem, and we have K, and this K is also related to the solution. So is there some technical to deal with that kind of problem? Actually, I think that case is inhomogeneous PDE case. Yeah.
Look, you will not be able to obtain fundamental to this moment. We don't know after that. To this moment, you will not be able to obtain fundamental solution except for linear partial differential operator. Okay. Once we have any parameters, any forcing term, nonlinear term, or something like that, the best thing is to deal with it using the reciprocity or analog equation. I prefer to use analog equation because it's very, very, very efficient. And there are a lot of vast area in exploring in this area. So
okay,
no way, we have to combine, as you said, you said this, not me. You combine part is analytical and another part is numerical. And instead of having 100% analytical and not 100% numerical, like finite element, this finite element, this is boundary element. Actually, it's not 100%. You say 99 because we integrate on the boundary also. Okay, but we can get is much better to use 80% analytical and analytical plus 20% numerical.
Yeah.
In analog equation method, I can assure you get not even 80%, you get 90% analytical. So your approximation will be within 10% or something like that. And this is the main difference between Dewey reciprocity and analog equation. In Dewey reciprocity, it is allowed for you to approximate. And me with Professor Chand and Professor Goldberg, we try to decrease the approximation. Okay? Instead of using something like in heat equation, for example, in Laplace domain, for example, you will end up to nabla square minus lambda square equal to something, okay, equal to domain term or something like that. So you can cut here and using this as body force. But with Chan, we did this. We cut here and we use this one part, only part as body force. So you improve the accuracy, okay? But in analog equation actually is much, much better. And actually analog equation using technique inside it to combine the finite difference and the reciprocity actually. Actually, it's not. It is approximation or numerical approximation of particular solutions.
Okay. Yeah. So I agree with that. Yeah. The part analytical. Yeah. Part numerical. Yeah.
Even with finite elements, we can in finite elements. A finite element is said we can obtain in boundary integrals and we can get the rest on the domain of the element. It is something like in between, like fundamental solution based finite elements is very promising, very, very, very promising, and still a lot of stuff needs to be done in it. Actually, if we have 20 guys, they want to do to go for this area, we'll have a lot of vast area to explore.
Okay, thank you. Yeah, and so any other question?
Hello, Professor. I would like to know how the boundary element method there is no longer problem.
No longer, no, I can't hear. Can you say it again? Boundary element method is
non-linear problem.
I think the nonlinear.
Nonlinear problem.
Yeah.
Yeah.
Okay.
The definition of nonlinear problem.
Just first look. Boundary elements is capable to model nonlinear problems. The only way you will get this is you will have your linear problem ui of xi plus integral tij of xi and x uj of x equal to integral for uij of xi and x tj of x. This is a linear problem. What you will need, you will add domain integral to either stress-based or strain-based. For example, you can have a kernel sigma ijk, kernel like this between xi and x times epsilon jk. This is the linear strain at point x, and now point x here is on the domain. And this term, you will need to discretize the nonlinear parts inside the domain. Instead of this one, you could have strain-based integral of the domain epsilon ijk asterisk of xi and x times initial stress jk. Okay, either this one or this one. Okay, because of that, you will need to discretize the domain to match the non-linearity inside the domain. Because of that, they say boundary elements can't work in non-linear. No, it can work in non-linear, but you will need some domain discretization. But from 2 years ago, I did with Muhammad Kamal. I think Muhammad Kamal was us. Now I don't know whether he's with us or not, but I see it at the beginning. We did very good thing is to introduce inclusions to represent the nonlinearity. For example, if your domain is like this one, for example, if you have beam like this, and this beam is you apply load here, something like this, so the nonlinearity start here in this area. So we'll test the points here. Once a point violates the nonlinear behavior, we introduce a small inclusion to allow damage for this one, and we couple a CUFE-BE inclusion theory with the boundary integral equation. Then again we add another inclusion here and here, and so on. So you'll end up to having discretization on the boundary and inclusion inside the domain, series of inclusion inside the domain. Okay, so you can represent the nonlinearity. But this one we need complete lecture. It will need at least 2 hours to explain what is the meaning by initial stress, what is meaning by initial strain, CUFE-BE inclusion theory, how to combine both of them together, how to make this iterative solution, and how to make incremental load analysis. Okay, this is very fast. So boundary elements will work in nonlinearity, but you will need some domain discretization. The amazing thing. For example, with this nonlinearity, you will get Ku equal P infinite element. Okay? Believe me, we were able, with this inclusion in boundary elements, we are able to get this K, the nonlinear K, infinite element, but after, for example, the K infinite element, you will get the K, part of it on the boundary, and part of it inside the domain. Okay? Part on the boundary and part of it inside the domain. So if you condensate this matrix and eliminate the domain term, you'll get this part. You can do it in finite element. In boundary elements, we were able to get this one direct, without domain, without condensation. You'll get very similar to the one you obtain in finite elements, direct with this inclusion theory. I can explain this one in a separate lecture, but this will need 2 hours at least. So believe me, boundary elements can work in anything. Non-linearity, vibration, anything. Fracture modeling, optimization. We can spend something like at least 100 or 200 years from now doing optimization only in boundaries. And maybe we will not finish by that time. Maybe we will be finished.
Yeah. Okay.
Okay.
So Yeah, I think later we may have some during the lectures. You may mention the BM for solving the nonlinear, right?
None. No.
I mean
Can you say it again?
in the next lectures,
Okay.
you may introduce the BM for solving the nonlinear problem.
No. Next lecture, I need to transfer
You
the
have the plan or
nonlinear to
no?
the boundary. First, this is very important.
Okay. Yeah.
This is still in the basis.
Yeah, okay.
After that, we can go for nonlinearity. I think we need to go for dynamics first. Dynamic problem to explain the reciprocity and time difference. Then we can go for nonlinear application.
Okay. So.
Okay.
So any other question? Yeah, I think later you can have the time to introduce us more detail about
Sure.
the how to solving the nonlinear
maybe
problem. But I think
one time I will visit you in China to meet everybody face to face. I have never been to
I think the transform the nonlinear. Yeah. So yeah. I will, if possible, I will invite you to visit us.
I have a lot of friends in China. For example, Professor Wen, Pihua Wen, he was my colleague. We were doing PhD together, actually.
Really?
Yes.
So I know you are all staying the UK. But yeah, your colleague. Yeah. Okay.
Yes. I was with Toshiro Matsumoto. He was postdoctor at that time. Pihua Wen and Piotr Fidlaneski from Poland. He was postdoctor also.
Okay.
All of us,
so I think
Nadi Belassad, we shared the same office together.
I think I meet all these famous professors.
Yes.
In the BM conference, or the Professor Wen, and meet him several times. Yeah.
Yes.
And now he's in the China. So
yes.
Yeah, actually, the September. Yeah. He will organize a conference, BTAC.
Really?
Conference. Yeah.
Is this December?
No, not December. It's September.
September. Maybe I will join you
Yeah,
for something like this.
Yeah. Okay. So I will send you the information.
Yes, please. Okay.
Yeah. Okay. So. Okay. Any other question? If no, let's thank the professor again, and
thank you.
Probably we
see you next week.
all you there next week.
Okay.
Yeah.
Thank you.
Okay.
Bye.
Okay. So bye. Yeah. Have a nice day.